All right, so people are still getting food and can continue to go through the line and have a seat. It's a real pleasure to introduce our speaker today as part of our AI-SDM seminar series. It's Professor Doron Cohen, Assistant Professor in the Department of Engineering and Public Policy here at CMU. And Doron came to CMU a little over a year ago, I think. And so I know a lot of folks in our community have been interested and have expressed to me their interest in interacting with him and hearing about his work. So we're happy to facilitate that today. Dr. Cohen is a behavioral scientist, and his work is really focused on the intersection of human decision-making, policy, and technology. So definitely some really relevant themes to our institute and some of the work that I'm sure that all of you are involved with as well. So he's done a lot of great work, has a lot of great ideas. I'll go ahead and we'll get things started. Thanks for closing that door. Please join me in welcoming Dr. Cohen.
Thank you very much, and thank you all for coming, for having me. I've been following this seminar series from the get-go, and I'm really excited to give this talk and appreciate the invitation. Thank you. So, as Mom said, I'm a behavioral scientist. I always have this slide as my first slide, a very kind of brief introduction. So I did my PhD at the Technion in Israel in behavioral sciences, and a postdoc at the University of Basel in Switzerland in economic psychology. Then I joined the DPP last September. And the vision that I want to advance in my work here and also before is an aim to try to better understand human behavior. So I'm a psychologist, a cognitive psychologist by training, a behavioral science by application. And what we focus on is trying to understand, why do people do whatever they do? I want to extend that to studying systems and complex systems that people interact with and behave within. And this is a two-way process. I want to better understand human behavior by better understanding the systems that shape it. And through better understanding the systems, we'll better understand the humans. And through better understanding the humans, we'll understand better how to shape and address different issues in systems and how to best design systems through rapid technological change, as is relevant to this crowd. So that's what I want to do. I want to better understand human behavior by better understanding the systems that shape it. What I'm going to do today is give a brief overview of the approach I'm trying to sell to you with a few illustrative examples, and then dive a little bit deeper into a project I'm doing on human-AI interaction, taking the perspective and the approaches I'm going to talk about now. So just to try to better define what I mean by systems, imagine yourself going to see the doctor. So I would define that as a closed-form system where we have the patient with their own information, incentives, and motivation and goals. We have the doctor that sometimes have a different set of space of options, of motivation, of the potential incentives, and their information available to them. But that's not all. We also have regulators and policymakers determining the constraints on that system and the procedures, the regulation, the norms, and the feedback that the system itself gives to those decision makers. So this describes a complex system with multiple agents and multiple constraints. What I want to do is use basic research to clarify the different components of the systems and how, through interaction and repeated learning, they shape they shape the system's outcomes for those decision makers, and how changes to these systems affect whatever the people do within them, and how that determines the final outcome. By the way, if anyone has questions, please stop me immediately. Ambiguity is an enemy of understanding, and I want everyone to understand. So just feel free to shoot any question you have. So today I'm going to talk about this final point. The success of most systems often depends on how people adapt and react to them. Any objections? I think most of us can agree on that. And I study exactly that. So it's a kind of a trivial truth that while many technologies have made the world a better place, others might not have worked so well, worked out for the decision makers, but also for the general public society, however you want to call it. And we're going to give two illustrative examples. One is what I call a buying using gap. And the second are cases in which safety devices backfire. These are intended to be a kind of a general examples for a phenomena where it doesn't matter so much the objective truth of the technology. It matters how people interact and adapt to the systems. And we'll later make some connections with AI. And these are kind of more general. So the buying using gap refers to kind of a paradoxical, well, not really a paradox, but a puzzle in mostly behavioral economics and economic research, where people buy a product for extra cost or a service or some device or technology. And by the fact, the action that they put their good money on the table, more money that they should to buy a product, they show us their emergent preferences. So now I know what people want to do by looking at what they buy. But then when you look at how people actually, or whether people actually use a technology or device or a service, you see that their preferences could be completely reversed, or the emergent preferences. The interpretation becomes impossible if you consider both buying and using as indications of what people really want, or what people understand, etc. I'll give you one example that I like, detachable radio panels. Now, I'm old enough to remember these, but I understand that not everyone is my age. Detachable radio panels, I'll explain what they are. In the past, around early 2000s, maybe late 90s, when you bought a car, you didn't get it with a fixed built-in radio set like today. Basically, you got the car without a radio. All you had is a hole, a niche, somewhere around the glove compartment. And you bought a radio set separately as a kind of a box, and that would be installed in the niche. And then you use the radio. The problem was they were very easy to steal.
Wasn't the whole point? I remember I had one of those things that I would take it out of the car every time I parked and carry it inside so that nobody would break my windows to try to steal my car.
Exactly. So the radio sets were very easy to steal. So to combat that, manufacturers came up with this technology, detachable radio panels, which are basically the panel of the radio where all the buttons are. You could separate it from the box by a press of a button. The idea was that when you leave the car, you take it with you, and then no one would break into your car because they would not be able to steal the radio. So this is a very effective technology that does exactly what it's supposed to do, deterring radio theft and car break-ins, right? So they were extremely popular. Most people bought them in the early 2000s. In a study by Yechiam et al., 2006, most Israeli drivers said they bought these radio panels for extra costs. But then the same drivers, about 2 weeks later, stopped using them completely. So you bought a technology for extra costs because it works so well, but then you never use it. That's a puzzle. We have a bind using gap. And why is that? That is something I want to explain, but I try to do it a little bit later in a few slides. Let's keep it as is, as a puzzle. Now, we can also learn from other technologies where at least initially people were reluctant to use them, despite the fact that they are very effective, but other interventions did help by reducing this gap. One example are seatbelts. So seatbelts, at least initially, a lot of drivers were very reluctant to use them, despite the fact that they are very effective in doing exactly what they are supposed to do. One thing that helped, of course, was having mandatory use rules and having punishments for not wearing a seatbelt. But another thing that really helped are seatbelt reminders. These annoying alarms that go off when you don't buckle up while driving. These significantly increased usage rates of seatbelts, showing that there are ways, or maybe we can learn something from it, how to reduce a bind using gap. Now, I'm not going to explain it yet. I just want to have it as an example. Now I want to show you the next example. Cases in which safety devices backfire. And here I have a historical example, the Davy lamp. Anyone heard about the Davy lamp? So the Davy lamp was at the time hailed as one of the greatest technological innovations of the early industrial revolution, one that helped kick it off, in a sense, and everything that came later. What it was a miner's safety lamp. So around the 1815, there were a lot of coal mine explosions, and a commission set up by the British government came up with a very large prize for the person that would come up with a solution. And one of those persons, the person that actually won this competition, was Sir Humphrey Davy, was an English innovator. And what he developed is a safety lamp that reduces significantly the chance of explosions. Before that, coal miners would use a naked flame as a light source. Now, coal mines are filled with methane gas that, interacting with a naked light flame, you have a big explosion. What Sir Humphrey did is encapsulate the naked flame within a kind of a metal mesh that is very close to the naked flame, and this reduces the temperature immediately around the flame, reducing the chance that the methane gas would interact or would achieve a temperature high enough to react and explode. So this was a very effective technology that did exactly what it did and objectively made the world a better place, a safer place. What happened? Well, coal mine explosions actually increased, reaching a peak in the 1860s, well after these Davy lamps and other safety lamps were very much entrenched in the coal mining industry. They were only later reduced by basically a public outcry that forced regulators, policymakers, and maybe most importantly, mine owners to invest more in better technologies, such as for better air circulation, more safety training, etc. So that was the result. Better safety, worse outcomes. Why did that happen? So I have some explanations and a model that I'm going to explain later. But my initial explanation is that now that we made the world a better place, a safer place, that allowed the actions by miners and, again, maybe more importantly, mine owners, to go into more dangerous places, like mine shafts that otherwise you would never explore and never work in for higher immediate rewards, but you also increase exposure to the risk, increasing the frequency of accidents and bad results. But is this a kind of a natural law that anytime you introduce a technology that improves objectively a task, making it safer for errors and accidents, would people always adapt and react in a way that increases risk exposure and leading to worse results? My answer is no. For example, airbags. Airbags in cars are not likely to increase risk-taking. My explanation to that is that they do not make risky actions more rewarding in the perception of the driver, the experience of the driver. When do airbags work, or where do you experience airbags as helping you? Only in very rare cases in which you're actually in a car accident. And even then, you're very likely to get injured in some way. So the experience of actually having them work is not really rewarding or reinforcing for the decision to take extra risks. I'll get back to that also. So starting with these two illustrative examples, I said to myself, starting my academic journey, I want to understand why do they happen, how do I explain them? But more importantly, I don't just want to do it in hindsight. Explanations, post-hoc explanations are well and fine, but you don't even have to be wrong, right? Any explanation can capture that. I want to be able to predict these effects at the system level before they happen, to better be able to design systems that are safer and more effective. So my starting point was looking into basic decision research. So what do we know that can help explain these phenomena? And I started from mainstream research, prospect theory, models that some of you probably heard about. And for example, prospect theory have focused on predicting people's reactions and behaviors when faced with fully described prospects. A prospect is a set of options that are fully described to decision makers in the sense that you know their whole outcome distribution and probability for each outcome. And this is one example from the seminal paper of prospect theory, where people are asked to choose between these two options, where option A gives you $3,000, let's say, dollars with certainty, 100% money on the table. Option B is a risky lottery that pays out $4,000 with probability 80%. Otherwise, you get zero, that is with probability 20%. If I would be a rational agent, of course, I should choose the option with a higher expected value, which is option B. Expected value, you just calculate the weighted average of probabilities and outcomes, sum it up, you get the expected value, and that's higher for option B. What do you think? What would you choose? Who would choose option A over option B? All right, we have some takers. Option B, who would choose?
There's nothing irrational about risk aversion.
Right, but we do have some risk-loving people that would choose option B. What do you think most people choose?
A.
That's right. Most people choose option A, about 80% in the classic study common interest. So this is preference for option A, safe, risk aversion. What would happen if I change the sign? So same problem. Now you choose between incurring a loss of 3,000 or a loss of 4,000, but only with probability 80%. Otherwise, you don't lose anything. Now what would most people choose? That's right. Most people not choose B.
I just thought that, I don't, there's nothing irrational about this.
I didn't say it's irrational.
Then why are we talking about it?
Okay, let me tell you. So how do mainstream research explain this? Not by irrationality, of course, by probability weighting. So that's my
You don't need that. If I gave you a choice between a hot fudge sundae and a kick in the pants, you would pick the hot fudge sundae. And then I said, which one do I want you to take away? So can I take away from you the hot fudge sundae or the kick in the pants? You say, I want you to take away the kick in the pants.
I'm not sure.
It's higher on gains if you just add a negative sign, the bigger thing is now the bigger loss.
Let's just wait on good and just be angry.
Yeah, we can do that.
There is a question online. Jennifer Chase is asking, would it not depend on how much value the money had to you?
Yes, so reference point, of course, is a major point in decision research. This is an illustrative example of one of the assumptions made by mainstream decision research and prospect theory, that people behave as if they overweight rare events. how does that explain this phenomena? And these are just two examples that can be captured by the assumption that people overrate rare events. Of course, there's a set of other experiments that have also been used to show this assumption or are captured by this assumption. So I'm just showing these two examples as illustrative for this, overweighting rare events. Here, if I overweight rare events, that means I'm more inclined to think about this outcome from the lottery of 0 as a little bit more probable than it is, or at least behave as if I believe that. That makes option B much less alluring if I think getting this 0 is maybe even higher than 20%. While with the loss problem, getting this 0 becomes a really good option for me, a really good outcome. Inflating this in my mind makes this option looking much better. Gretchen, do you agree?
Yeah, I like it.
Okay, so that's why I'm showing this problem, not about irrationality, overweighting rare events, that's the point. And that's the assumption of mainstream research. So that's it, right? We can go home. We know that people overweight rare events. We can explain any system by mainstream research because it's so good at capturing human behavior. But then I said, as a second thought, I said, really? How about using detachable radio panels? So a rare event there is getting your radio stolen or getting your car broken into, right? If people inflate or behave as if they inflate this option, they should really love taking the detachable radio panel with them and use it. So we won't see a bind-using gap. They should wear seatbelts for the same reason. They should not take more risks with safety devices because the rare event, the bad rare event of a coal mine explosion should be inflated in their minds. So these phenomena go against this mainstream assumption that people behave as if they overweight rare events. And in fact, what I found is that early research, earlier than the classical seminal work by Kahneman and Tversky, actually questioned the prediction that people overweight rare events. In this paper by Slovak, Baruch Fischer, also from EPP, and Sarah Lichtenstein, they looked at or tried to explain why do people are reluctant to wear safety seatbelts. And their model implies that people, rather than overweight rare events, people are actually much more likely in tasks where they have experience with interacting with the system, and the system gives them feedback, either reinforcing or they experience friction, people are much more likely to behave in the opposite way, as if they underweight rare events, deflate in their mind the probability of a rare event, and behave as if they believe it won't happen to me. So the task of wearing a safety seatbelt, usually we go on a drive, we wear the seatbelt, we pay the costs, maybe very minimal, but there are some costs for wearing a seatbelt that we experience. We never experience the rewards, or we almost never experience the rewards. That leads us to put much more weight on these frequent unreinforcing outcomes from trying to wear the seatbelts. Experience teaches us that we do something, we never get rewarded for it, we really shouldn't do it again. So to try to clarify this kind of theoretical puzzle, I ran the following experiment. What I did, they had participants go through 60 different choice tasks. And a choice task is like this. 2 options, choose one of them. And they follow the same kind of classic Kahneman and Tversky prospect theory type of problems with a fixed kind of probability distribution, but for each problem, the numbers were different. Right? So you play through 60 different choice problems. This is how it looks. Online game, 2 buttons, full description of the prospects. So if you choose A, you get 59. B is a lottery with a bad rare event because you can lose whatever you could have gotten had you chosen option B. After each choice, I give you feedback. What you chosen, what you got from that choice, and what you could have gotten had you chosen the other key. This is a foregone outcome, a full information paradigm. Okay. Now the trick is, each of the 60 different choice problems, first, it's fully described. Second, you only play it once, and then you play another new problem. So this feedback, what you gotten from your action, what you could have gotten, is completely useless. It doesn't teach you anything new about the world. You already have all of the information in the probability distributions. And in the next round, you're going to play a new problem. So why does it help you with this feedback? It shouldn't affect your choice. So what did we get? Yes.
Does it help you do the math? Because many people won't be able to compute 60 times 0.98 plus 10 times 0.02. And so just empirically they'll figure out, hey, this is better or that.
The experience?
Yeah.
How? It's only you see it once. You see 59
They're
and
just
60.
doing the math that, hey, this roughly this magnitude of quantity with this probability is better. Right? The person won't be able to sit and compute the expected value here. But after having gone through many such examples, you might get an idea as to what's.
But each problem is different.
Yeah, they might get a good heuristic of how to compute.
So how do we said in the paper that this experience does help you understand the task better, right? So you do something, you see what happens, right? But other than that, mathematically, I'm not really sure it helps you calculate anything. And the classic decision science that we're trying to kind of debate with, they do assume that you at least subjectively transform these numbers into a prospect theory, for example. You do understand it. Our criticism in this paper, by the way, is that people really don't understand, believe, or trust this information, right? But other mainstream theories like prospect theory do assume that, right? So at least by the definition of the mainstream decision models, the experience is completely useless. So, I'm going to show you the results. You have a question?
Yeah, I'm just curious how different the problems are. Like, is it just the probabilities and quantities that vary? Is the structure the same?
The structure is the same, expected value differs slightly. Some problems, option B has a higher expected value. Some problems, option A, some the same expected value. We randomize them and have the same kind of quantity for each participant. The structure was the same, the numbers were different.
Sorry, and each participant just do one cross.
No, so they play through 60 problems in random order.
There's no learning effect.
That's what I'm going to show. So here are the results. These are the B choice weights, so choice of the risky option. The X is experience with the task. From the first problem you play to the last problem you play. So more experience further along the X-axis. Initially, people don't have any experience, they just follow the description of the task. And here we see that most people prefer option A over option B, it's lower than 50%. That means this aligns with the prediction of prospect theory, mainstream research, as if people overweight this bad small probability. And then with experience, feedback from the task, we see a complete reversal. That is, with experience, people behave as if they underweight the relevant rather than overweight it. Complete reversal in preference. Now, this reversal for the what we call probability weighting in this decision science world, but basically is whether you overweight or underweight, is just one example of how experience changes the underlying predictions of mainstream models. In fact, a lot, if not most, of the predictions of mainstream models like prospect theory either are eliminated or reversed when people actually have experience with a task. And this is known as the description experience gap. Now, my current favorite model to explain how people behave when they actually have experience, which I think are the most interesting problems in real life, is that first people choose actions that minimize the probability of immediate experience regret. So for example, in this problem, when I choose option A, 98% of the time, option B will give me 60. So 98% of the time, I would regret choosing option A. Regardless of expected value, of my understanding of the probabilities, just this experience. I call this immediate regret. And the second robust phenomena is that people behave as if they believe that it won't happen to me, underweighting rare and extreme events. And this simple model, this is a verbal model. I was just going to hand wave it away, but there are formal definitions of exactly how it works and why. Not going to go into that though. This formal model predicts just the buying using gut if we assume that buying a service or a product is from description. So maybe I follow a TV ad or what a salesperson tells me or what a friend described. But then how I actually use it is from experience. And when I carry around this detachable radio panel, I'm almost never rewarded for it because the car won't get broken into. The radio won't be stolen. My experience tells me this is completely redundant. I have to think about it a little bit more to say, okay, of course no one stole it because I took the radio panel away, but experience doesn't teach me that. And with safety devices, so the data lamp makes risky actions, such as going into a much more riskier shaft, much more frequently rewarding. I might regret not going in when my friend just made a lot of money going in, or a mine owner using a shaft that they wouldn't use, but they make more and more money by taking these extra risks now that they can with the extra safety. Again, increasing the exposure. Sometimes that's a very bad decision. Yeah.
For the radio panel thing, is there any data on second purchases? By this I mean that somebody bought this detachable radio, and after a while maybe the radio got spoiled, right? And they were in the stage where they decided to not take it out.
Yeah.
But then when they're buying again, would they still buy the detachable one or not?
That's a great question. I'm not sure, and I think the world changed too fast to really test it. So it was I think a decade or so, or maybe less, that you actually bought them, and I'm not sure that people changed the radio set so much. That's a good question. I don't know, maybe.
There's another question in the chat. I'm just gonna read it out. Is the experience of each problem actually useless? Or does the result mean that participants start out not trusting the system or experimenter, and then learn along the way that the system isn't rigged, and they are better off choosing the riskier option, higher risk, higher reward? Or even that they start perceiving the system is rigged, even if it isn't, and they are better choosing the riskier option?
I think that's a valid model of behavior that aligns with what I'm trying to say, that experience does matter, even when it's from a mathematical kind of economical analysis shouldn't matter, or from the perspective of the models we try to criticize in this paper. So the world that we are trying to kind of address, the issues we're trying to address, is in relationship to models like expected utility theory, prospect theory, and others that do not have any kind of learning component and say experience shouldn't affect behavior in any way. And we show that's not the case. And the model from the chart, I think that's a valid model that goes along with this idea.
Just a quick question regarding your previous slide. You mentioned that like probability is more, it is easier to be like, if you want to choose an action that minimizes probability. Is it because probability is easier to perceive? Like it's easier for participants to compare the probability of when it happened versus the other?
So maybe there's a confusion. I want to clarify that this way of saying this allows, that's just how the model is built. So I want to predict behavior. I don't have access to all the set of experience that you have as a participant. So just seeing this problem, the settings, I'd say, okay, 98% of the time you might regret choosing option A. That's why you should choose option B. But from your perspective, the black box that makes you choose whatever you choose, I don't think that you follow the probability, you follow the experience. I know this confusion comes because I haven't formally defined the model, but I just don't have time to do that. Okay? So that's my favorite model. How does it help with human AI interaction research? So I want to argue that basic research, like I showed before, can shed light on important human AI puzzles. And one example that I try to tackle in my work is the tendency to over-rely on AI, automation bias. And when does it happen? And how we can predict it, and what should we do about it as system designers? I have a lot of criticism about the research ongoing in behavior and psychological science that a lot of the time doesn't define where the constructs, like what is automation bias, I have no idea still. And that it focuses on individual differences rather than system design features. That's what I want to do. I understand systems, individual differences are hard to change and address. And so first of all, I try to define a type of automation bias, which I call automation shirking, and at least a little bit more formally, something that I can understand. And what do we do about it? That's basically what this is about. So it's a preprint, currently under review, so feedback is great. And yeah, these are my collaborators, Yefim Roth, Marcus Schobel, and Jorg Rieskamp. So in this project, we look at specific systems, human automation or human AI redundancy systems. These are not recommendation systems, they are not decision aids, they are decision systems. The automation itself can make actions that change the outcomes of the system itself. It doesn't just give you more information. We think this is where the future, or the near future even, is going to. And a lot of attention and resources into this type of work. These are just examples from the medical domain that gets a lot of attention. And in this project, we asked two questions. First, how do different designs affect operators' behavior, human operators' behavior, in a redundancy system? So redundancy, think about two components, redundant to each other, independent, and making the same action on a system, like an engineering concept. And how to best design and manage such redundancy systems. And we're going to use basic research to try to tease out the fundamentals of these systems. Rather than looking at the complexity of real life, we want to see the basic drivers. Some examples, radiologists and AI reading X-rays. So we have an AI feedback system that can also make decisions like asking for a second review and second opinion, and the doctor itself looking at the X-ray and trying to make their own independent choice. Drivers and semi-autonomous cars. So the semi-autonomous car system can also stop the car if it detects an emergency. That's what makes it semi-autonomous. And we also have the driver as a redundant safety system that also can brake the car. And another example are students with ChatGPT. So some students write assignments with ChatGPT. So they ask the chat to produce a product, an output. Then it might be the case where the chat and the student would double check the output, looking for errors and mistakes. Over-reliance on the chat in this case would be to copy-paste whatever it gives you without even reading the text. No one does it, of course, at least not at the So yeah, we focus on decision systems. Now, I hope I convince you that people often adjust their behaviors in unexpected ways. When we change the system, we have reaction from people. In our study, we tested and developed, and that's what I'm going to show you now, a controlled paradigm. Again, basic research, abstract research, where we use idealized conditions with no cognitive or time pressures, where checking the outputs and doing your job, which is basically checking the outputs, is cheap, easy, and fully incentive compatible. We also control operator-specific aspects, like trust traits, skill, expertise, situational awareness, workloads. Those are off the table. They are the same in all our conditions. What we test is just one thing. Does design alone change behavior? And I wanted to explain the actual experiment. First, what are the designs? What are the conditions we tested? So first, we have a control condition without any AI or automation. A single operator working alone. So imagine some process like X-rays coming into your laptop. You're the human operator. You need to make a decision. Then your decision determines the outcome in accordance with the actual state of the world. In parallel operator design and redundancy design, human operators and automated operators work simultaneously. So for each process step, time step, you have the decision by each operator made simultaneously and then determine the outcome at the same time. That means there's no interaction or feedback between the operators, only post hoc. And the third one is serial operator, where they work serially. In our experiment, we wanted to see this effect. So operators, the first operator, the automation always comes first. Then the human operator, unlike in parallel, they see what the automated operator decided to do before they make their own decision. And in fact, in a very recent meta-analysis in Nature Human Behavior, more than 95% of current systems are serial. Right.
How do you aggregate decisions for the second phase? Like the decision of the human network, how does that result necessarily? As you said, you're like terrible.
Yeah, I'll show you the test.
Oh, sorry.
It's just a general design. We have these three conditions. And yeah, any questions about this aspect of design? So participants play these over multiple rounds, and in each round we have a task. So I'm going to explain that. And there's full information, full feedback after each choice. About 100 participants in each condition, between subjects, yes. So this is the task. So in each design, in each condition, participants play through multiple rounds. In each round, they make a two-stage decision. First, I want them to decide whether they check or skip. That's it, a binary choice, either check or skip. If you check, I give you a reliable current estimation of the current state of the process. The process follows a Markov chain, will be in either a safe or an unsafe risky state. So if you check, I give you an estimation of the current state. But checking is costly. You have to pay me something to get it. If you skip, you don't get the information. But regardless of your first decision, your second decision is an action decision. What do you do about the process? Do you stop it or let it run? If you stop the process and it is in a safe state, you get a false alarm, you have to pay me something. You get a small loss. But if you stop it and it's actually in an unsafe state, you get a correct rejection and a salary, reward. If you let it run and it's safe, that's a hit, you get a salary, a reward. But if you let it run and it's actually unsafe, then you get a very large punishment, a cost, a loss. Okay? This is how it actually looks in the experiment. So let's say trial one, this is a single check condition. First, skip or check. Let's say I skip. Next decision, I don't get any information. I just tell you, hey, you chose to skip the safety check. Do you report unsafe or safe for the current round? Let's say I report unsafe. The round ends and I get feedback. What I reported, what was the actual state, what is the outcome? Okay. What if I decide to check? In one variation of the study, the check gave a numeric evaluation. The numeric evaluation was drawn from a normal distribution with a known safety margin range. If the number was within the range, it turned out green, and that's a safe state. If it turned out outside, it was red, that's an unsafe state. Later variation, we just said safe or unsafe, that's enough. And we got the same results. So now I have safe, I report safe, and that's my outcome. See that my points are lower because they paid for the check. 1 point. These points are later converted to real money, real losses. What happens if I report unsafe, but the world is safe? Just for the example, now I have a false alarm and I have some small loss. Now, this is a single condition. In parallel, you basically have exactly the same flow, but the feedback now changes because you play the same game with an automation. The automation follows the same path. It checks and then reports whether the world is unsafe or safe. That's what it does. Okay? So here in the feedback for the parallel condition, after I make my own choices, I get to see what the automation reported, in this case also safe. What was the outcome? What is my reward? And you do that. In the serial condition, the only difference is now the other checker report is shown to you on the first screen before you decide whether you check or sleep. That's That's a difference. Now, playing with this automation, that's just to compare, that's other conditions. Playing with this automation is a very good idea because automations are actually quite competent, but they are imperfect. As experimenter, I manipulate the probability for the AI to be wrong. On average, it's about 50%. That means that some people it's very high, some people it's very low. I wanted to look at the continuous effect of this probability and whether people adapt and react to that. But on average, it's a very competent but imperfect AI. Our dependent variables, first I'm going to look at how much people actually check in the preconditions, where I make sure, based on the incentives and the information that participants have, that checking is actually the optimal decision to make in all conditions. And I calculate the expected proportion of misses based on the system that you interact with. That's what I'm going to show you. So just to sum up, in my experiments, you can have accidents, misses, which are costly and rare. The AI is competent but imperfect. Checking costs are very small, and you should always check. And I'm not going to go into the whole probability number. So we pre-register the predictions that we're going to see automation shirking. People shirk more with automation, lower checking rates in the double check conditions, that's both parallel and serial, and higher expected accidents rates in the double check compared to the single check. So the world becomes less safe, even though the AI is perfectly competent. And this follows Kasparov's law. I think I'm going to miss, I'm not sure I have a lot of time, but anyone heard about Kasparov's law? Gary Kasparov? Well, Gary Kasparov is a really smart guy, and he wrote a book about his experiences playing with AI systems in chess. And he said that in a closed system like chess, where everything is known, the space is finite, a weak human with a machine or AI and a better process will always be superior to a strong human, strong and weak in the sense of chess, with a machine and an inferior process. So it's all about the process of playing with AI. It doesn't matter how strong you are as a player. And in this experiment, we try to come up with a more general case. So in systems where machines are error prone and humans must be part of the decision loop, still, a human and a machine and a process that is incentive aligned would be superior to a human alone, which both might be superior to a human and machine with bad incentives. What do I mean by bad incentives? Let me show you the results. So these are the three conditions. We're going to compare checking rates and expected accident risk. First, checking rates.
Clarification question. From the point of view of the human operator until they make the decision, what's the difference between the single and parallel?
None.
Nothing.
You know, though, that you play with automation, you go through a tutorial, you see its outcomes, you know its parameters. Yeah.
Okay, but the rewards also, it's the same.
It's the same, but you do have on the very first round is exactly the same, but then you get feedback. So from round to round, actually the information you get is the same as serial rather than single. Okay? At the end of the round of the thing. Checking rates 0 to 100, single, parallel, serial. In single, we got a nice result. We wanted people to check. We made the experiment so that it's good for them to check, and they did. In parallel, people check as much as they do when they work alone, which is good. So here, you check the same rates, you have a good AI working with you, outcomes become much better. But in the serial, people actually check about 20% less, checking significantly more. So the serial system increased the accident risk. It was enough to make objectively the system worse than parallel, but also in some cases worse than having just a human playing alone. These are the expected accident risks. Yeah.
What's the point of having the AI system if it doesn't save me work by allowing me to check less often?
Think about a nuclear power plant and you're a safety inspector, right? So rather than working less, you want to keep the power plant safe.
Or increase accuracy but not decrease effort, is that the idea?
As redundancy features in a system that are designed to reduce error rate, not make your life easier. So you're doubling the work.
Increase accuracy, not reduce effort.
Think about double checking by nurses, right?
Mm-hmm.
So you're doubling the work, but there's a reason for that.
Got it.
Right? So serial condition led to automation shift. In study 2, we said, okay, in most cases, people can actually decide which kind of system they work with. And they can put themselves in a world where they first see the AI feedback or not. So we let them decide. In this, this is a within subject condition. In each round, you first choose whether you want to play serial or parallel, and then you follow through the same task as before. We predicted that people would prefer the serial system, then check significantly less. That's exactly what we got. So first, most people chose the serial system most of the time. Then they checked significantly less, leading to more accidents and results. So people self-selected, actively selected themselves into a condition that previously led to worse results, but then also checked much less.
They had more accidents, but what's the profit dynamic between the working alone and working with machine?
Here so what's the optimal advantage of that?
Yes, we have a score.
Yeah.
And I can lose more, so I have more accidents, but I can also make more points because I'm making less costly checks.
Yes, but we did design the incentive system such that the accidents are costly enough so that you would always check, especially here when you're just choosing between these two AI systems, where the cost of checking does not trade off the risk of accidents. So we specifically made the system and the information that you have such that you should always check. We made checking cheap enough, basically.
Okay.
Yeah. But it's certainly that's the model that we developed. Checking costs are really important. If you increase checking costs of the friction, people will check less, definitely. So people actively prefer systems that encourage automation checking. Now, study 3, I'm not going to go into, I'm going to skip it. So the model we developed is an opportunity cost model to explain it. So we say, okay, all else being equal, people seem to perceive the value of a check as less when they have early feedback from the AI system telling them everything is fine. Don't do it. The same happens when you increase checking costs. So we call it the automated decisions observability before you make your own decision, and that affects the perceived utility from checking, how valuable checking is for you, or how much opportunity cost you perceive in the task. That affects whether you check or not, and that's also there's some feedback loop that you might learn that checking is actually more valuable than you initially perceived. So, takeaways: human operators check less than optimal,
the starting point, especially in serial systems where automation feedback increases opportunity cost of effort. And human operators prefer the serial system, which leads to inferior performance compared to parallel, but often compared also just to the single condition. And with low reliability systems, when we know the AI is not perfect, but is not close to that even, the redundancy conditions, where you have two operators, may lead to more accidents than single operators. And we show that in a formal way. So to sum up, I want to offer you an engineering approach to decision research. We want to understand behavior in the systems that shape it and develop behavioral research as a science of design. With prediction-oriented models as practical tools, robust problem-based behavioral insight, we want to understand real people and real problems in context. And the final line here is what I'm developing this work into. So we got an INSF grant for it. And the idea is life is not an experiment. Experiments are good to highlight the most important features of a task or paradigm. And we're gonna leverage that to test behavior in real life, such as radiologists reading x-rays with AI in serial versus parallel condition, manipulating check-in costs, probability of success, and stuff like that. And that's it. Any questions?